Welcome to this lecture on how TRIZ AI can revolutionize the design of microcapsule materials for advanced cosmetic applications. This is going to be a fun journey through innovation methods, materials science, and smart problem solving. First, let's understand what microcapsules are. Imagine a tiny chocolate shell filled with liquid caramel. A microcapsule is essentially a tiny sphere with a shell enclosing a core. The shell is a protective barrier, usually made of polymer, and the core contains the active ingredient like vitamin E oil, fragrance molecules, or moisturizing agents. In cosmetics, microcapsules protect delicate ingredients from degradation by air, light, or water during storage. Then, when you apply the product to your skin, the capsules break open and release their contents exactly when and where needed. Think of them as tiny delivery drones for your face cream. But instead of flying through the air, they sit patiently in the cream until they're rubbed or warmed by your skin, then pop open to release their payload. Now let's talk about TRIZ. TRIZ stands for the Theory of Inventive Problem Solving, developed by Russian engineer Generative AI. TRIZ is a systematic methodology for innovation. Instead of random brainstorming, TRIZ uses patterns from millions of patents to solve contradictions. The core idea is that most engineering problems have already been solved somewhere else in a different field. TRIZ helps you find those proven solutions and adapt them to your specific problem. TRIZ works by identifying contradictions, which are pairs of requirements that seem to oppose each other. For example, you want something to be strong, but also lightweight. Let's identify the key contradictions we face when designing microcapsules for cosmetics. Here are 4 major contradictions. First, capsules must be soft enough to feel pleasant on skin, but mechanically robust enough to survive manufacturing and storage. Second, stable for months in the jar, but releasing quickly when applied. Third, biocompatible so they don't irritate skin, but chemically protective, so they shield reactive ingredients. Fourth, impermeable to keep ingredients inside, but breathable to allow controlled release. These contradictions seem impossible to solve all at once, but TRIZ provides specific principles that have been proven to resolve such conflicts across thousands of inventions. The first TRIZ principle we'll use is local quality. This means making different parts of an object perform different functions. Instead of a uniform shell with the same properties everywhere, we create gradients or layers where different regions have different characteristics. This is a gradient shell microcapsule. The outer layer is rigid and protective for storage stability. As you move inward, the shell becomes progressively more flexible and water-soluble, allowing faster release when it contacts moisture on your skin. Think of it like an orange peel. The outer surface is tough and waxy to protect against damage, but as you go deeper, the peel becomes softer and easier to break apart. Principle 2 is composite materials. Combine different materials to get the best properties of each. Here's a multi-layer core shell architecture. The outer layer is a flexible polymer for comfort. The middle layer contains nanoparticles, like silica or clay, for mechanical strength and barrier properties. The inner layer is a different polymer that's compatible with the core ingredient. This is like wearing a winter jacket with an outer waterproof shell, a middle layer of insulation, and a soft, comfortable lining on the inside. Each layer does its own job perfectly. Principle 3 is phase separation. Create regions of different phases within the same structure. In a phase-separated shell, we have a polymer matrix with distinct hydrophobic and hydrophilic domains. The hydrophobic blue regions repel water and protect oil-based actives. The hydrophilic red regions swell when they contact moisture, triggering release. This elegantly resolves the impermeable but breathable contradiction. Water molecules can pass through the hydrophilic channels, providing breathability. But oils and other actives stay trapped because they can't cross the hydrophobic domains. Principle 4 is controlled porosity. Introduce pores of specific sizes and distributions. A porous shell has tiny nanopores distributed across its surface. The pore size determines what can pass through. Small pores allow controlled slow release of small molecules. Larger pores can be triggered to open by mechanical stress or temperature. Pore size is critical. For diffusion-controlled release over several hours, pores of 5 to 50 nanometers work well. Smaller than that, and release is too slow. Larger, and you lose your sustained release benefit. Let's do a quick back-of-the-envelope calculation for diffusion time through a porous shell. The diffusion time scales as L squared divided by D, where L is the shell thickness and D is the diffusion coefficient. Let's say the shell thickness L is 1 micrometer, which is 10 to the minus 6 meters. For a small molecule diffusing through a polymer, D is roughly 10 to the minus 10 meters squared per second. So the diffusion time is 10 to the minus 6 squared divided by 10 to the minus 10, which equals 10 to the minus 2 seconds, or 10 milliseconds. That's extremely fast. But if the pores are partially blocked, or the shell is 10 times thicker at 10 micrometers, the time scales to 1 second. If the shell is 100 micrometers thick, diffusion takes 100 seconds, about 2 minutes. This simple calculation shows how shell thickness directly controls the release rate. Thicker shells mean slower, more sustained release. Thinner shells give you burst release. Now let's think about mechanical stress. Can the shell survive being stirred in a cream or rubbed on skin? When external pressure is applied, the shell experiences stress. We can estimate this using the thin shell approximation. The stress in the shell is approximately pressure times radius, divided by 2 times the shell thickness. Let's say the pressure is 1 kilopascal, which is about 10 times less than atmospheric pressure. The capsule radius is 10 micrometers, and shell thickness is 1 micrometer. The stress is 1,000 pascals, times 10 times 10 to the minus 6, divided by 2 times 1 times 10 to the minus 6. This gives 5,000 pascals, or 5 kilopascals. Typical polymer yield strengths are 10 to 100 megapascals. Our calculated stress of 5 kilopascals is much lower, so the capsule will easily survive normal stirring and handling in the cream. But if you deliberately want the capsules to burst when rubbed on skin, you design them to fail at typical skin shear stresses, which are around 10 to 50 kilopascals. This requires a thinner or weaker shell. Now let's talk about stimuli-responsive release. These are smart capsules that release only when triggered by a specific stimulus. The main stimuli used in cosmetic microcapsules are pH, temperature, light, and enzymes. Each offers unique advantages. pH-responsive shells use polymers that swell or dissolve at a specific pH. Since skin pH is around 5.5, slightly acidic, you can design capsules that are stable at neutral pH in the jar but release when they hit the acidic skin surface. Temperature-responsive polymers like poly-N isopropyl change from hydrophobic to hydrophilic above a transition temperature. You can tune this to be around 32 degrees Celsius, which is close to human skin temperature. Below that, they're collapsed and impermeable. Above that, they swell and release. Photoresponsive capsules contain molecules that cleave or change shape when exposed to UV or visible light. This can trigger shell degradation and release. Useful for sunscreens where you want release upon sun exposure. Enzyme-responsive shells are designed to be degraded by enzymes naturally present on skin, like esterases or proteases. This ensures the capsules release their contents only when they're in contact with living tissue, not sitting in the jar. So we've used TRIZ to generate innovative concepts. Now let's bring in AI as a complementary tool to accelerate the design process. The first major task for AI is searching, clustering, and systematizing the vast scientific literature on microcapsules. There are millions of papers and patents on polymers, surfactants, emulsions, colloids, and cosmetic delivery systems. AI tools can rapidly search these databases, extract key information, and cluster related concepts together. Natural language processing models can read thousands of abstracts, identify key materials like chitosan or alginate, extract synthesis methods and performance metrics, and organize everything into searchable knowledge graphs. This saves researchers months of tedious manual literature review. It also reveals hidden connections between different fields. For example, a polymer used in drug delivery might have perfect properties for your cosmetic capsule, but you'd never find it without AI-assisted search. The second task is using AI for modeling and parameter optimization. AI can build models that predict how capsule properties like size, shell thickness, and composition affect performance metrics like release time, stability, and mechanical strength. Machine learning models can be trained on experimental data from published papers. They learn to predict diffusion coefficients, swelling ratios, and mechanical moduli for new polymer combinations that haven't been tested yet. This allows you to virtually screen thousands of possible formulations in minutes on a computer, identifying the most promising candidates before you spend time and money on actual lab experiments. Let me give you a concrete example: predicting final capsule size from processing parameters. Capsule size depends on many factors: stirring speed, surfactant concentration, polymer concentration, and temperature. A machine learning model can learn the complex nonlinear relationships between all these variables and predict the final capsule size distribution. You train the model on existing experimental data, either from your own lab or extracted from published papers. Then the model can suggest optimal processing conditions to hit your target capsule size, say 10 micrometers, plus or minus 2. The third task is using generative AI to create draft figures, schematics, and structured explanations. Generative AI tools can take a text description of your capsule structure or release mechanism and generate a draft schematic diagram. They can also produce structured explanations of how the system works, which you then refine and edit for scientific accuracy. This dramatically speeds up the creation of presentation slides, research proposals, patent applications, and teaching materials. Instead of spending hours drawing in Illustrator, you get a draft in seconds that you can refine. Of course, you must always carefully check and edit AI-generated content. AI makes mistakes, especially with technical details. It's a powerful starting point that saves time, not a replacement for your expertise. Now let's see how TRIZ and AI work together in an integrated workflow. Here's the complete workflow. Step 1. Clearly define your design contradictions using TRIZ thinking. Step 2. Apply TRIZ principles to generate innovative concepts. Step 3. Use AI to search literature for relevant materials and methods. Step 4. Use AI modeling to optimize parameters. Step 5. Build physical prototypes and test them. Then iterate, based on results. This workflow combines human creativity and systematic innovation from TRIZ with the computational power and massive data mining capabilities of AI. You get the best of both worlds. Let's work through a real design challenge. We want to encapsulate vitamin C, which is notoriously unstable and degrades in water and air. The problem is that vitamin C, ascorbic acid, is hydrophilic, so it dissolves in water-based creams. It's easily oxidized by air and light, and it's pH sensitive, degrading at neutral or alkaline pH. We need to protect it completely until the moment it's applied to skin. The key TRIZ contradiction is, the shell must be water impermeable to prevent vitamin C from dissolving and oxidizing during storage, but it must become water permeable quickly upon application so the vitamin C can absorb into skin. The TRIZ solution uses both gradient structure and pH-responsive materials. The outer layer is made from a hydrophobic polymer that's completely impermeable to water at the neutral pH of the cream, around pH 7. The inner layer is made from a pH-sensitive polymer that remains solid at pH 7, but rapidly dissolves at skin pH of 5.5. Now we turn to AI. We ask it to search the literature for suitable pH-sensitive polymers with transition points near pH 6. AI finds candidates like eudragate polymers, certain chitosan derivatives, and alginate-based materials. It extracts dissolution rate data from papers. Next, AI builds a simple model of shell thickness versus dissolution time. We want the inner layer to fully dissolve within 30 seconds of skin contact. The model suggests an optimal inner layer thickness of about 2 micrometers with a specific polymer composition. Here's the final design. The outer hydrophobic shell keeps water and oxygen out during storage. When applied to skin at pH 5.5, the inner layer dissolves in seconds, exposing the vitamin C core to the slightly acidic skin environment where it's more stable and can penetrate. The result is a capsule where vitamin C shelf life increases from just a few days in a normal cream to several months. Yet when you apply it to skin, the vitamin C is released quickly and absorbed efficiently because the pH trigger is immediate. Let's explore one more advanced concept: self-healing shells. During manufacturing, transportation, or storage, microcapsules can develop microscopic cracks. These cracks cause premature leakage of the active ingredient, ruining the product. TRIZ has a principle called self-service, which means making an object repair itself automatically without external intervention. The solution is to embed tiny capsules of a healing agent within the shell material. When a crack forms, it ruptures these nanocapsules. The healing agent flows into the crack and polymerizes, sealing it shut. This concept is inspired by biological self-healing mechanisms in skin and bone. When you get a small cut, your blood clots and seals it. Here, we mimic that with synthetic chemistry. The healing agent could be a monomer that polymerizes on exposure to air or moisture. I can search for suitable healing chemistries already proven in other fields like self-healing concrete, protective coatings, and elastomers. Then we adapt those chemistries to be biocompatible and safe for cosmetic use. Let's visualize how these capsules are actually made. The most common method is interfacial polymerization. You create an emulsion of oil droplets in water, or water droplets in oil, then trigger polymerization at the droplet interface to form the shell. Start with an oil and water emulsion. The oil droplets contain your active ingredient. You stabilize the emulsion with surfactants. Then you add a polymer precursor that reacts at the oil-water interface. The polymer reacts and forms a solid shell around each droplet. Now you have microcapsules. You can wash away excess surfactant and polymer, then incorporate the capsules into your cosmetic formulation. The key process parameters are stirring speed, which controls the initial droplet size, surfactant concentration, which affects emulsion stability, and polymerization reaction time, which determines the final shell thickness and cross-link density. AI-based optimization can tune all these parameters simultaneously. You run a few pilot experiments, feed the data into the model, and it suggests the optimal combination to hit your target capsule properties. Once you've made your capsules, how do you characterize them to confirm they have the right properties? You need a suite of characterization techniques. Microscopy, like SEM or TEM, shows you the capsule morphology and shell structure. Dynamic light scattering, or Coulter counter, gives you the size distribution. UV-Vis, or HPLC, tracks release kinetics. AFM, or compression testing, measures mechanical properties. FTIR, or NMR, confirms chemical composition. And accelerated aging tests predict shelf life. AI image analysis can help with microscopy, automatically counting capsules, measuring sizes, and detecting defects. AI can also analyze release kinetics data to extract diffusion coefficients and fit mathematical models. Before any cosmetic product reaches consumers, it must pass rigorous safety and regulatory requirements. Every single material in your formulation, including the capsule shell polymers, surfactants, and active ingredients, must be on the approved list for cosmetic use in your target markets, like the EU or USA. You must perform skin irritation and sensitization tests to ensure the capsules don't cause allergic reactions. Any degradation products from the shell must also be non-toxic and non-irritating. AI tools can screen your proposed chemical structures against databases of known allergens and toxic compounds. This saves time by filtering out problematic candidates before you even start lab work. What does the future hold for microcapsule technology in cosmetics? One exciting direction is personalized cosmetics. Imagine capsules that are custom-tuned to your individual skin pH, temperature profile, or even your skin microbiome composition. I could design formulations specifically for you based on a skin scan. Multifunctional capsules could co-encapsulate multiple active ingredients that are normally incompatible. They would release sequentially, one after another, to deliver a complex treatment regimen from a single product. Smart sensing capsules could change color or fluorescence to give you visual feedback. They could tell you when the actives have been fully released, or warn you if the product has degraded and is no longer effective. Bio-inspired capsules might use natural peptides, proteins, or even engineered living cells as shell materials. These would be fully biodegradable and could have dynamic, adaptive properties that synthetic polymers can't match. Let's recap the key TRIZ principles we've applied. Local quality led us to gradient shells, where properties vary smoothly from outer to inner layers, resolving the soft but strong contradiction. Composite materials inspired multi-layer architectures and nanoparticle reinforcement, giving us both flexibility and mechanical robustness. Phase separation created shells with distinct hydrophobic and hydrophilic domains, allowing selective permeability and resolving the impermeable but breathable contradiction. Controlled porosity gave us nanopores that enable tunable diffusion rates, letting us dial in exactly the release profile we want. And self-service led to self-healing shells that automatically repair cracks, extending shelf life and reliability. Now let's recap how I accelerated the entire process. I performed literature searches and knowledge extraction that would take a human researcher months, completing it in minutes and revealing hidden connections across disciplines. I built predictive models that let us virtually screen thousands of formulations, optimizing parameters like size, thickness, and release rate before doing expensive experiments. And AI generated draft schematics and structured explanations, dramatically speeding up the creation of presentations, papers, and teaching materials. The real power comes from combining TRIZ and AI synergistically. TRIZ provides the creative, systematic framework for identifying fundamental contradictions and generating innovative concepts that break through conventional thinking. AI provides the computational muscle, massive data processing, and rapid modeling capabilities to validate those concepts, optimize them, and fill in the practical details. Together, they form a complete innovation pipeline that takes you from abstract principles and contradictions all the way to concrete, optimized, manufacturable designs ready for the lab. If you're a student wanting to apply these methods, here are some practical tips. Always start with crystal clear problem definition. Write down exactly what you need your microcapsules to do, what properties are required, and what contradictions you're facing. This clarity guides everything that follows. Use TRIZ tools like contradiction matrices and the 40 inventive principles as sources of inspiration, not rigid rules. Let them spark ideas, then adapt those ideas to your specific context. Take advantage of free AI tools. Use ChatGPT or similar models for literature synthesis and brainstorming. Use Semantic Scholar or Google Scholar with AI-assisted search. Use open-source Python libraries for building simple models. Always draw diagrams, either by hand or with simple digital tools. Visualization is absolutely key to understanding complex structures and mechanisms, and to communicating your ideas clearly to others. Do quick back-of-the-envelope calculations as early as possible. Even rough estimates give you physical intuition, help you understand scaling laws, and catch conceptual mistakes before you waste time on detailed modeling. Iterate rapidly. It's better to test 10 small ideas quickly and learn from failures than to spend months perfecting one big idea that might not work. Fast iteration with feedback is the essence of good engineering. Let me leave you with some final thoughts. Microcapsules are a beautiful playground for applied material science. The structure of the shell, down to nanometer details, determines the properties like permeability and strength. And those properties enable the function you care about, like controlled release. TRIZ teaches us that innovation doesn't have to be random or mystical. By thinking systematically about contradictions and applying proven principles from other fields, we can reliably generate breakthrough concepts. AI amplifies our natural human capabilities. It lets us process vast amounts of information, explore enormous design spaces, and quickly validate ideas that would take forever to test manually. But remember, human creativity, scientific judgment, and domain expertise remain absolutely essential. AI is a powerful tool that makes you faster and smarter, but it's not a replacement for deep thinking and careful experimental validation. The future of materials innovation lies in this synergy, combining uniquely human insight, intuition, and creativity with the raw computational power and pattern recognition of AI. Thank you for joining this lecture. I hope you're inspired to apply TRIZ and AI thinking to your own projects in materials, science, cosmetics, or any field of engineering. Remember, every great innovation starts with a well-defined contradiction and a willingness to think differently. Good luck, and keep innovating.